In the previous video, I showed how if the compression zone was entirely in the flange, you could use all the equations and procedures for a rectangular beam except for AS min. Right? We talked about how if the concrete area is in the flange, how things change. And so now what I want to do is talk about what if you have beams and slab poured together. Yeah, you see how that looks like a T-beam? Can we count the slab as part of a T-beam with the beam? And the answer is yes. And what we want to do is know how much of the slab width we can use as the flange. And since it's not an isolated T-beam, we call it B effective, EFF or effective. And so obviously it makes sense that if you go from the middle to the next neighbor, that makes sense. It would be effective. You go halfway to the next beam on both sides. And that's this, center to center. But the other thing is, if you have a situation like this, where you have the beams like really far apart like this, it might not be reasonable to take all the way to the midspan between the beams as part of your flange. And what you do is, if that's the slab thickness, okay, HF, you can count 8 slab thicknesses, okay, as an ear for your T-beam. And so what that means, so let me try to draw that. There we go. If you got 8 slab thicknesses on both sides, and that's the B of the web, the total width, the total B effective will be the width of the web plus 16 slab thicknesses, because 8 on each side. And lastly, this one is kind of confusing for many people. So let's see if I can draw this. So you got this T-beam, and then you got this span length going like that. And this distance to the next support, so from this support to the far support, we'll call that L. It takes some time for the compression zone to expand out. And so this width that's in compression with, okay, so the width of the slab that participates can't be more than that span length over 4. Okay, so that span length over 4, okay, is the participatory width of the slab, the part of the slab that contributes to the beam as a T-beam, so L over 4. So you have center to center, 16 slab thicknesses plus the web, or L over 4, you take the least of these 3. Okay. What about if you're on the very last beam and you have only one ear? It's very similar. You get the minimum of all the way over to the center of the next beam, but only on one side. The ears, if you have only one side, instead of 8 slab thicknesses, are 6. Okay, so, and it's only on one side, so B web times 6 slab thicknesses, and it's span over 12, not span over 4. And so in this very special case, on this last beam on the end, you would get the least of these 3 things. And that would be effective for that sort of T-beam. It doesn't look like a T really, it looks like a upside down L, but we call it a T-beam. Okay, and finally, what if you do have a T-beam that's not part of a slab and T-beam combination, slab and beam combination, it has a different sort of requirement. There is a minimum thickness for this if you're going to build something like that. So that thickness of the slab needs to be bigger than the width of the web over 2. Okay, and this total width here, BF needs to be less than 4BW. Okay, so there we go. Those are all the requirements. And so what we'll do next, when the compression zone is totally in the web, that's very, very similar to everything we've done, except, as I said, with ASME. But this example here, where the compression zone goes into the web, is a little different. So we'll talk about that in the next video.